So, as you know, we just completed 60 years of the Institute, and also we are celebrating the 75th year of Indian independence as part of Azadi Ka Amrit Mahotsav. So today's talk will be given by Professor D. Indumathi. Before I hand over to the chair, Professor Meena Mahajan, I have a couple of announcements. This talk is being live streamed over YouTube, and the audience in YouTube can ask questions by putting those in the comment section. One of our volunteers is actually monitoring those questions, and at the end of the talk, your questions will be conveyed to Professor Indumathi and she can answer. So with that, over to Professor Meena Mahajan. Meena.
Yeah. Welcome everybody. It's my great pleasure to introduce today's speaker after having started off saying that she really needs no introduction. But I hope that this talk is going to reach an audience far and wide. And so therefore, let me say a few words about the speaker, Professor Indumathi. She works in the area of high energy physics, which is kind of on the border between experiment and theory, an area called particle phenomenology. And she is interested in both strong and weak interactions as a way to probe the nature and the properties of fundamental particles. She's been interested in studying neutrinos from various sources, and she's been one of the founding members, a very active member of the proposed India-based Neutrino Observatory project. In fact, she's currently on the scientific management board of this project as well. One thing which I should highlight is that Indumathi is an alumnus of our institute. She completed her MSc in physics at the Madras Christian College and then came to IMSc to do her PhD. And post-PhD, she spent quite a bit of time as a postdoctoral fellow at various places, including PRL Ahmedabad, Dortmund University, Germany, IISc Bangalore. And then she joined HRI in Allahabad for a faculty as a faculty member. She was there for a few years. She finally came back to IMSc sometime in the late 90s to rejoin as a faculty member. She's very keen on science popularization, as all of you who have been here for some time already know. She's been a very active member of the Tamil Nadu Science Forum. She's the editor of a children's magazine which has been running since 1993, the Jantar Mantar. And some of you probably already saw an earlier event where some of the old issues of Jantar Mantar were, excerpts were extracted from there. So she publishes regularly. She's an editor of this magazine and writes articles regularly for this magazine. So as you can see, science popularization is something very dear to her heart, and today she's going to give us this popular lecture on how the sun shines.
So good afternoon. I'm very happy to be here to see all of you in person. This talk is not going to satisfy any audience, so I might as well say it right in the beginning. I've tried to keep it self-contained. I've tried to introduce some very simple notions in the beginning, and as it goes on, I will try to introduce something a little more advanced, but I think it is still going to be too elementary for maybe 99% of this audience. So anyway, with due apologies, I hope that somebody out there who's listening on YouTube will actually enjoy the talk, but I hope that you will enjoy it too. So with that introduction out of the way, let me start. So as I already said, I'm going to showcase how the sun shines to talk about particle physics, which is the area I'm interested in. We start out by asking about matter and radiation. So I want to make a few remarks before we begin actually about the sun. Matter, we all know matter. Here I am, made of matter, standing on a stage which is made of matter and looking at a screen which is made of matter. And traditionally in school we talk about solids, liquids, gases, and if you're a little careful you will add plasma to it as well. And so that's what we think of, particles which are made up of atoms or molecules, and that's what matter comprises of. And if you look at radiation, so the most important or common radiation that we know is light. People think of radiation as nuclear radiation, but this is not necessarily true. You can also have many other, I will show you in a moment, things which are actually, which comprise radiation. And as an example, light is made up of waves, in contrast to matter, which is made up of fundamental elements called atoms. So light said to have a wave nature, and that has been known for over 100 years now. And what do you mean by a wave nature? There are two properties that we have in a wave. So the one thing to remember is that a wave propagates both in space and in time. So when it propagates in space, these ups and downs which form the wave, the separation between two ups or two downs is called the wavelength, lambda. And if you plot the same thing as a function of time, then the distance between two ups or two downs is called the time period t, and the inverse is called its frequency. And there is a very defining relationship between the two, which is that the velocity of the wave is given by the product, frequency times the wavelength. And if you have the special wave, which you call light, then for light, there is a constant speed actually, or velocity, the modulus of that. It has a name, it's called c. Its exact value is now defined because in fact the meter is defined through this quantity, and basically it's about 10 power 8, few times 10 power 8 meters per second. And this c is something that we will see again and again in our talk. But this is the meaning when you say that something has a wave nature. It is defined through its wavelength and its frequency or inverse time period. So this is the kinds of radiation which I took off from NASA. I'm sorry that it's not visible. In fact, it's not visible to me as well. So you can see that all the way from microwave ovens to infrared, the remotes, down to actually what you call nuclear radiation. All of it is called radiation. And the funny thing about radiation, although I will here focus only on light, though I said that light behaves like a wave, it also behaves like a particle. And when it is a particle, or it shows its particle nature, it is called a photon. And this is called a quantum of light. You must have heard of quantum mechanics, which defines objects at the very, very small levels, at the very, very small scales of distances. And in fact, the discovery of this photon, or this quantum, or this particle, which is the particle form or nature of light, led to the birth of this quantum theory. And of course, Einstein was involved in it, but it's not so critical. Okay. So light, which can either be described as a wave or as a particle, is said to have a dual nature. And after this understanding came the second understanding that actually electrons also have a dual nature. Though we think of an electron as a point particle, it's an object which is sitting inside the atom, and it goes around the nucleus, all those things that you learn in school. But we've also seen that electrons can behave like waves and show wave nature. That is, I can associate a wavelength with the electron, and it is a very special kind of a wavelength, because a matter particle like an electron has a wave nature only if it is moving. So if it has a momentum p, then it has a wavelength associated with it, which is proportional to the inverse wavelength. So the larger the momentum, the smaller the wavelength, and this proportionality constant is called Planck's constant. It is a number. You can look it up, you can find out what it is. The inverse relationship is the most important part. So you can see that when the momentum goes to 0, then the lambda is not defined. Okay, so that means here I have thought of the universe as being made up of matter and radiation. But now matter particles like electrons have both particle and wave nature, and radiation like light has both particle and wave nature. So let us see what this means. And this is, as I said, this is the basics of the basic elements of what goes into defining the quantum nature of our universe. And so let us see where this leads. So this is one important fact that we need to remember about wave nature of electrons, or in fact all particles. Now, of course, how can Einstein be left behind? One of the most important or the most famous equations. And in fact, let's ask this question: what does E equal to mc squared actually mean? So here we introduce a new concept. It's the antiparticle. Just like I have an electron which has minus charge, I have a positron which has the same mass m but the opposite electric charge. So I've put it as E plus over here. And when matter and antimatter, for example, E minus and E plus collide, their mass is completely converted into an equivalent energy, pure energy form, in fact photons, and that equivalent energy is mc squared plus mc squared, which is twice mc squared, where c is that same number which I defined earlier, which is the speed of light in vacuum. So there are some technical notes throughout the talk. So this is for a little more advanced audience, so you don't have to really worry too much about it. It's just a note on units, because I might be talking about units. A very natural unit in particle physics is a million electron volts, where an electron volt is a very, very small quantity in terms of joules, so unit of energy. and the mass of the electron in this equivalent energy units, mc squared, is about half an MeV, whereas the proton's mass is about 1000 MeV, which is called 1 giga electron volts, or GeV. So you will see this number MeV and GeV throughout this talk. Okay? The technical note too is something that I really don't want to talk about, but apart from this concept of antiparticle, excuse me, Dirac introduced another new idea called spin. And we have seen this in chemistry, for example, when we talk about electrons being fermions, spin half particles in some units, natural units called h/2 pi. And you have the Pauli exclusion principle, which defines how electrons can fill into the orbits or in atoms. Okay, so there is this notion of spin of a particle, and there is this notion of antiparticles. And with this, I think more or less I have defined the quantities that I want to use, and therefore I will come back to my first question: how does the sun shine? So this is I'm sorry, the credit for this photograph is not visible. So let us ask the question: how does the sun shine? So this is something that has been asked actually for years, not just from 1854. It is a subject that has fascinated people for centuries. And excuse me, there have been various theories about the source or the origin of the solar energy, because I think generations of people who have just looked out of the window and seen the sun see something which is very similar to what it looked like yesterday or the year before or a decade before or even half a century before. And the question is, what could be that source of heat which gives you such a steady state of or output of energy for so many decades or centuries or even longer? And that is a question that has troubled not only physicists like Helmholtz or Kelvin, but also a very unusual actor in the drama, which is Charles Darwin, who is more famous in biology than in physics. But Darwin had a very different reason to understand the age of the sun and the age of the solar system, because he needed the Earth to be at least 300 million years old to see the kind of diversity of species that was there in the Veld in England. And this number, 300 million years, was completely in contradiction to Kelvin, who said that if you have just thermal energy in the sun, it would not last very long. So really what could be happening in the sun was that a lot of, oh sorry, this is a spelling mistake, a lot of meteors keep falling into the sun, and the energy of these meteors falling into the sun gets converted into solar energy. And he had actually a factor of 10 smaller age of the sun, and said that Darwin has to be wrong. So whether Darwin is correct or whether Kelvin was correct, the question was of importance then and now, because of course without the sun there is no photosynthesis, there is no life on Earth, and obviously it's a very important question to ask. Okay, so let us see what has happened in the sun. So this is the question that is being asked. So in the beginning, we know that the matter, there's some matter in the universe, just hydrogen gas. And you can see one little blob over here, which is my attempt to show a higher density in the middle than on the sides. And the moment you have more material in the center than on the sides, gravity is an attractive force. And any small fluctuation which increases the density of matter in the center causes the gravitational pull to be even larger, and so the clump becomes even more, and so this attracts even more matter around it. And as it gets collates more and more matter towards it, that clump at the center gets more and more compressed. It's spherical because gravity is a symmetric force. And in fact, the one thing that people, especially I think in school, are not usually told, but it is a very important factor in how our universe is born and evolves, is that it is always attractive, because two like electric charges can repel and two unlike charges can attract, but gravity is always attractive. And so this force is always on, it's always compressing the matter, and as you compress the matter more and more, you remember that there was Pauli blocking between the electrons. This will get overcome, the matter will get compressed tighter and tighter, and you know that compressed matter becomes hot. And as the temperature of the gas increases to some particular point, then a new physics which Kelvin did not know about, which Darwin did not know about, which is called nuclear fusion starts to occur, and this nuclear fusion is the source of energy in the sun. So this is the one-line statement, which I will actually try to elaborate in the next few slides. As I said, Kelvin did not know about nuclear energy, so let us try to understand how nuclear energy plays a role in this fusion process. So we go back to 1920, we remember Einstein's equation, which was even earlier than that, E is equal to mc squared, and Aston in 1920 discovered a very interesting thing. A hydrogen atom is actually just a proton, because the nucleus of a hydrogen atom is just the proton, whereas a helium nucleus has 2 protons and 2 neutrons. So if you look at this, this has 4 protons, this has 2 protons and 2 neutrons, and a neutron and a proton are roughly the same mass. In fact, the neutron is a little heavier than the proton. So I would expect that the helium is going to be heavier than the hydrogen, 4 hydrogens, because the 2 neutrons here are 2 protons and 2 protons are the same mass, and the 2 neutrons are a little heavier than the 2 protons over here. However, Aston found that actually the 4 hydrogens are heavier than the helium, and this difference is because of something called binding energy, nuclear binding energy. This is the same process by which electron gets bound in a hydrogen to a hydrogen or to a proton nucleus and forms a hydrogen atom. The plus charge of the proton and the minus charge of the electron are attractive, and they bind together to form an atom. That's how all atoms are formed. And when this is formed, you have learned in school, for example, something called ionization potential. You have to give energy to the electron to take it away from the atom, right? And that's because it's comfortable being bound to the nucleus. Similarly, you have to give energy to break up the helium, and that energy is actually almost 1,000,000 times larger than atomic binding energies. And the reason for that is this little thing. It's a little technical point, so if you don't understand it, it doesn't matter. The size of an atom is about 10 power minus 10 meters, whereas the size of a nucleus is 100,000 times smaller than that. And there is a principle called Heisenberg uncertainty principle, which says that if the distance scales are smaller, then the energy scales are correspondingly larger. So if the distance or the sizes of the nucleus is 100,000 times smaller than the size of the atom, then the energies involved are 100,000 times larger, which is why nuclear reactions, nuclear fission, nuclear fusion processes give you so much more energy per atom than chemical reactions. Okay, so this nuclear binding energy, this is what Aston has discovered. People realized very quickly, Eddington, Gamow, Weizsäcker, Bethe, all of them realized very quickly that this could drive the fusion processes in the sun. So you can look at this a little bit later. It's not important. The relevant formula is over here. 4 protons convert to 1 helium nucleus that contains 2 protons and 2 neutrons, which means that 2 protons have converted into 2 neutrons, and therefore 2 plus charges are missing on the right hand side, and therefore I have to produce 2 plus charges to conserve charge, right? And these quantities, these 2 objects are the positrons that I talked about, the antiparticle of the electron. And then there are 2 more new particles which are called the neutrinos, which are the hero of the story. And this, you remember now, this million electron volts is the unit of energy that I'm talking about. This is the amount of energy released in this reaction. So I'm going to show it again over here. You can see that there are 4 objects which sit usually inside the nucleus. This is also a nucleus. This is technically called a baryon number. It is the 4 on both sides. There's 2 antiparticle of electron type, 2 particle of electron type, and this is called the lepton number. And there is 26.7 MeV to conserve energy momentum in the process. And the fact that energy is released means that it is an exothermic process. So this new particle is called the neutrino, and it has a little subscript called E, which I will talk about. Okay, I will talk about it in the next coming couple of slides, but the E indicates that it is somehow associated with the electron or the positron. Okay, so this is like a huge list of new particles that I have introduced, and I'm not going to read the technical note. And this new list of particles begs the question, yes, then we only know about protons and electrons. There are so many new particles you have introduced. What is the world made up of? So let's just go to add a slide to indicate how these particles actually fit into our current understanding of the universe, and how they fit into our current understanding of what makes up the universe. And the way in particle physics we think about it is that there are particles and their interactions. And a model of the universe should indicate how these particles interact with each other to produce the known physical universe that we know. It's a very challenging thing. People have only solved some small parts of it. Some parts are better known, some parts are still being studied, and then there are a lot of new hypotheses which are yet to be confirmed. But what we do know is that there are 4 fundamental forces. So gravity is very old. We all know about gravity. Anything with mass attracts, and as I said, they all never repels, always attracts. We know electromagnetic forces. We have learned about it in school. And these 2 new forces, strong and weak interactions, are best understood through our nuclear interactions. Strong interactions are what hold the nucleus together. We must ask the question, beyond the hydrogen atom, you have more than one proton in the nucleus, and the nucleus is very small. And both protons have the same charge, both are positive. So how can 2 positively charged particles be pushed together? Because they have to repel and fall apart. But the atoms are stable all the way to mass of some 200 and something. So how come you manage to squeeze so many protons in? That is because there is a strong attractive force which is larger than the electromagnetic force, which holds these protons and neutrons together, tightly bound inside the nucleus. And the way to understand weak interactions is through an example, and the example I will give is, for example, radioactivity. Everyone knows radioactivity. It's an example of a weak decay process. The fusion process in the sun is also another example of a weak decay process. So for example, a proton has electromagnetic interactions because it has a charge. It sits inside the nucleus, so it has strong interactions, and all particles have weak interactions. And if you look at the last line, the neutrino has no electromagnetic interactions because it has no charge. It doesn't sit inside the nucleus, so it does not have strong interactions. So if you want to study weak interactions, a very good candidate would be the neutrino because it has no other interactions. And weak interactions, the name says that they are weak. So therefore, if you want to study these weak interactions, which is hard to do, because you're more likely to see strong or electromagnetic interactions, then you have to study a very clean system like the neutrinos because they do not have any other kind of interaction. So this tells us why we are interested in the neutrino in the first place, and now we tell you the next little bit technical fact, but it's necessary for my talk. I have this neutrino with the subscript E, and there are actually 3 of them. They're called 3 flavors, and these flavors are called mu and tau. And along with these neutrinos, also there are partners of electron, E, mu, and tau, and these mu and tau are simply heavier versions of the electron. They have exactly the same properties except their masses are larger. And why they exist, whether there are more than 3 flavors or generations, all that is still an open question. We do not know the answer to this. But we do know that there are at least 3 flavors of neutrinos, and that will also play a part in my talk. So this nu E, okay, is what is emitted in the sun. And all these neutrinos were assumed to be massless earlier, but now we will soon find in our story that that is no longer true. And how do we know that only nu E is emitted in the sun? That is the rest of the story. So let us go to the solar neutrino experiments. So here is the sun really far away, and we are asking the question, how do we know that fusion processes occur in the sun? Maybe actually meteors are falling into the sun and that's what gives you energy, right? So we have to be able to establish this fact. So this was first done by Ray Davis and his collaborators. Although he had his results in the late 1960s, he started this experiment some 20 years earlier. And it doesn't matter what the process was. He had a huge tank of chlorine, which, some dry cleaning fluid which contains chlorine. And then he asked the question, this neutrino can convert the chlorine into the argon. Okay, by converting, see, you have here you have some mass number here. So the same number of protons and neutrons are there, but what happens here is that one neutron gets converted into one proton, and therefore the chlorine becomes an argon. So this is the reaction that is happening. This is an example of a nuclear transmutation, and it is called the charge current process because in this process the neutrino gets converted into an electron, so a zero charge particle gets converted into a minus charge particle. So the charge changes in this interaction. So we will call it RCC. And what he found is that there were many estimates of how many neutrinos come from the sun. And he found that he had only 1/3 of the expected events in his detector. So he was the first to see neutrinos from the sun, but he saw only 1/3 of the expected rate. And there were a lot of criticism of his experiments because he could not guarantee that these neutrinos actually came from the sun. What if there were other unknown sources of neutrinos on Earth and they were all conspiring to do something else, or he had got something else wrong? So there's a very important experiment by the Japanese which did a very simple experiment. Just scatter the neutrinos on electrons. Where are these electrons? You take a huge tank of water. Here. You take a huge tank of water, 2,000 tons of very, very pure water, and water contains a lot of electrons, and you just scatter these neutrinos on those electrons in the water, and then what do you see? You will see that if you plot the events as a function of, this is not clear, this is cos of theta, where theta is the instantaneous angle with respect to the direction of the sun. So as the sun moves in the sky, when you see an event, you look back and ask, where was the sun at that point? Draw the line from the sun to that point, and that angle with respect to that is theta, and you can see there is a huge peak in the forward direction, which means that this is some background which is coming from other sources, but most of the neutrinos are actually coming from the sun, and in fact they were the first to show that these neutrinos indeed come from the sun. So this Kamioka experiment showed this, that the sun does shine due to nuclear fusion, but instead of 1/3 that Davis got, they got half the number of expected neutrinos. So there is still a puzzle. So there are sun shining due to nuclear fusion, there are neutrinos from the sun, but in both the experiments the rate was lower than expected, and after a long discussion and lot of confusion, the answer was attributed to some exotic properties of the neutrinos and not due to the wrong calculation of how many neutrinos comes from the sun. And the solution, which is, I'm just going to cut that long story short, is due to something called neutrino quantum oscillations, and that is what I am going to talk about next. You remember that I said there are 3 types of neutrino flavors, nu e, nu mu, and nu tau. So here, let me take the example, just simple example of only 2 flavors, nu e and nu mu. And are the colors faded out? Can you see that they are different colors? Is it possible to now switch off that light? So there are 2 colors, nu e and nu mu, because I can't see, this is supposed to be red and this is supposed to be blue. So suppose I say that nu e and nu mu are not pure particles, but they are made up of combinations of other particles called nu1 and nu2. And in this, thank you very much. And in this way of looking at it, I look at the wave nature of these particles, which is why I started out the talk talking about the wave nature of these particles. Thank you, that looks more like the original. So when I look at the neutrinos as a wave, now I say that these nu e can be thought of as comprising 2 different waves with some coefficients such that cos squared theta plus sin squared theta is equal to 1. What does this mean? It means that the probability that nu e will be seen either as nu1 or as nu2 is 1. The neutrino cannot be lost anywhere. Similarly, nu mu is also the same thing, except that it is an orthogonal combination of those 2 states. So let me start out by saying that the neutrino is coming from the sun. The nu e type neutrino, let's say, contains some fraction of red and blue, which is the nu1 and nu2 states. But if these 2 have different masses, then what will happen is that over time they will separate out, and at this point, for example, there is no red, so you will see only nu2 state, and if you look at this point, there is no blue, so you will see only nu1 state, which means that depending on where you put the detector far away from the sun, then you might see different combinations of nu1 and nu2, which means that you will not see the total nu e coming from the sun, but only a fraction of it, depending on what the value of theta is and also what the mass differences between nu1 and nu2 are. So this is the theory of neutrino oscillations. It allows a flavor to leak into another flavor. So if your detector is only looking at nu e, some of the nu e has been oscillated away, that's what it means to oscillate away into another flavor, has been oscillated away into a different flavor. What you have left is a smaller fraction than 1, and therefore the rates were less than expected. And when you do this, and there are some more technical details with a very beautiful experiment from Snow, which I don't want to talk about, and you will find that everything comes out consistently, and now today people believe that indeed neutrino oscillation is the correct reason for the kind of solar neutrino behavior that you see, and many experiments around the world have actually confirmed this fact. So here it is, our present understanding is that there are solar neutrinos, they have been seen, but these solar neutrinos exhibit neutrino quantum oscillations, and also they are non-zero mass, and this is new physics beyond the standard model, and people are therefore looking for oscillations in other sources of neutrinos. And one source of neutrinos is actually from our own atmosphere. Our atmosphere is full of neutrinos, which very originally are called atmospheric neutrinos, and these atmospheric neutrinos are what in fact we have been actually trying to study or explore by raising this possibility of having an underground neutrino detector in India called INO, the India-based Neutrino Observatory. So let me then go on to talk a little bit about what INO will do. So I don't want to tell you any very technical details. So what we have is that it is a very massive project. It's one of the mega science projects of India, jointly funded by DAE and DST. And what it wants to do is it wants to create an underground laboratory which will do neutrino physics, but such a lab can be used for many other future experiments as well. Okay? In fact, there is the particular detector that we propose to do to install over there to study neutrinos is called the ion calorimeter or the ICAL detector. So we have had a very successful INO graduate training program with many PhD students, some of whom are in this audience. So what does this detector do? It looks very small. Sorry. So it has 3 modules of just ion layers. So there are 56 millimeter ion layers, and in this gap you insert an active detector called the RPC. So what it does is that if a charged particle goes through the RPC, it gives you a signal in your electronics. So you pick up these signals, and as you go through, as a particle goes through all these layers, you get a signal, join the dots, and from the track that you have, and from the bending of the track, because this ion is magnetized, it's a magnetized detector, you will be able to understand certain properties of the particles, charged particles, like its momentum, direction, charge, everything. And from there you can try to go backwards and understand the properties of the neutrinos which interacted with that ion to produce these charged particles. So that in sum and substance is this detector. This detector is a proposed detector. A lot of simulations work has been done with it, and it's going to be humongous. Its magnetic field is very modest. It's just 1.5 Tesla, but these active detector elements are about 30,000, and it will involve about 4 million channels of electronics, which means it needs a huge industry interface, which has already begun. There are more than 50 industrial units actually working with our group, and I will maybe show you some pictures later. So I just want to show you some pictures of how we have been developing and doing the R&D, because it's a completely indigenous project. There is, every component has been developed here. So these RPCs are actually just flat plates of glass with a gas gap, which will then be put at a high voltage so that it will discharge when the charged particle goes through. So we started out by making 30 centimeter by 30 centimeter, 1 meter by 1 meter, until we reached the design goal of 2 meter by 2 meter RPCs, which needs a crane to hoist because it's so heavy. And then after that, we actually did experiments with the 1 meter by 1 meter RPCs. We did experiments with the 2 meter by 2 meter RPCs. And now, in fact, this is completely automated by industry, and this is an industrial unit where these RPCs are actually being manufactured currently. So this is how the R&D has evolved from the lab, and the handover has gone to the industry. Similarly, the electronics, you started out with very modest electronics, and now you can see that every component, there is a front-end electronics, back-end, data acquisition systems, everything is now state-of-the-art and has been indigenously developed. So this is the status of all the R&D that is going on. And the final thing is that there is a mini ICAL, 11-layer detector, which has been functioning in Madurai through the pandemic, in fact, very nice, and has taken a lot of data. I think 2 PhDs have already come out of it. So these are the ion layers, as you can see, and you can't see in between are the RPCs, which are kind of hidden because they are stashed inside, and you can see these copper coils around, which provides the current to generate the magnetic field in these ion layers. So that is the prototype detector, and you can see that this is taken last year, no, not last year, last year meaning 2020, so yeah, that's like maybe still 1.5 years ago. The years are going past. And this is, all the summer students who came at that time were helping to actually, this is the RPC, you can see now how big it is, 2 meter by 2 meter, and they were helping to slide it into the ICAL detector. And you can see like all the smiling faces having a lot of fun. So huge amount of student interest in this project, and especially from the local universities and colleges, from around, around Madurai and Tamil Nadu, and also students have come from all over India actually to participate. Some tracks, as I said, the dots, join the dots gives you the information on various things. And of course, what exactly will we learn from this detector is the physics, which I will not be able to tell you in this talk. I mean, that is a whole technical thing. We will learn some properties of neutrinos. There are some very important open properties of neutrinos, and the way neutrino physics, because underground experiments have a habit of being very challenging. Neutrino experiments are very slow counting experiments, and what you therefore need to do is have a combination of competition versus collaboration in the international arena. So you have a detector, other groups also have detectors, all of them are looking at neutrinos, but you're trying to find a different set of properties with different precisions than the experiments which are happening in the rest of the world. I guess everybody knows that this project has been severely delayed. We are still hoping that because of this magnetization of this detector, it's a unique selling point for this detector, and that this project will still have its place in the international setup. Well, that depends on how the project progresses, but anyway, so what exactly we will learn, I will not tell you, except to highlight once more what I had said, that you will see atmospheric neutrinos. And the kind of neutrinos, atmospheric neutrinos that you will see are the nu mu kind. You remember I said there were 3 flavors, nu e, nu mu, and nu tau. And nu e is what is emitted by the sun. And what happens in the atmosphere is that you have neutrinos and antineutrinos. Because you have neutrinos and antineutrinos, because these are antiparticles, neutrino when it interacts will produce the particle, which is the muon. The antineutrino when it interacts will produce the antiparticle called antimuon or mu plus. And because of the magnetic field, these two will bend in different directions, and by knowing whether you had a mu minus or a mu plus, you can tell whether you had a nu mu or a nu mu bar antineutrino induced event, and that is really the reason to have the magnetic field in the detector. And when you do this, and then you do your calculations, and you can understand a very important property of neutrinos which is not known. And just to say it in a very simple language, we know that in nu e and nu mu, I said I could write it as kind of a superposition of 2 states called nu 1 and nu 2, which had different masses. When you have nu e, nu mu, and nu tau, there are 3 of them. So obviously I must have 3 mass states, nu 1, nu 2, and nu 3. And although it's known that nu 2 is heavier than nu 1, it is not known till today whether nu 3 is heavier or lighter than nu 1. Okay? This is called the mass ordering problem. And INO, because of its magnetic field, is specially designed to answer this question. Okay? So that is really what we can find. That's just a peek. There are some details which I don't want to talk about because, as I said, the audience is very general. So we can, so this I called it the mass hierarchy, but this is actually the mass ordering. Okay? So here, that is all. So I just want to now end with 2 remarks, which are kind of rather long. So let me talk about, okay, so what have we seen? Neutrinos probe some of the most important frontiers of physics. So by the way, though I say outlook, practically every statement in this has not been talked about so far. I just try to squeeze it in because, there are so many facts about neutrinos and it's just one talk. So I try to kind of, like just give you glimpses of various things. So neutrinos probe some of the most important frontiers of physics, astrophysics, and cosmology. That is because there are neutrinos which come from our sun, from our earth, our atmosphere. Because the sun is like other stars, there are neutrinos coming from other stars and the cosmic background neutrinos. So actually neutrinos are coming from all parts of the universe, and so they probe actually not only all parts of the universe but all ages of the universe from the time the universe was born in the Big Bang up till today. Okay, so neutrinos, because they have only weak interactions, are the cleanest probes of weak interactions, which are least studied and understood today. So that is another remark for neutrinos. Neutrinos are the key to understanding many features about the origin and evolution of our universe. So one fact which I want to tell you is that if you look around, at our universe, and people have looked around the Hubble telescope, there are so many telescopes which have looked out to the furthest ends, which means the earliest, because we know that the velocity of light is a constant. So when you go further away in time, you're going to earlier parts of the universe. And when you probe earlier and earlier parts of the universe, you have seen more and more galaxies, but nobody has seen anti-galaxies. Nobody has seen antimatter stars. Whatever you see in the universe is actually dominated by matter. But we believe that the universe began in the Big Bang. And if the universe began in the Big Bang and then it evolved out from there, there must have been equal amounts of matter and antimatter. So where has all the antimatter gone? Or is our notion of the Big Bang wrong? So the only way to understand this discrepancy is to say that somewhere during the evolution of the universe, some force or some interaction caused the antimatter to evolve away, leaving only a matter-dominated universe. And so far, this difference has not been found, this difference in interactions has not been found in electromagnetic or gravitational interactions. A small possibility is there in weak interactions, and it is possible that the neutrinos could hold the key to understanding this fact. And that is another reason to understand or to study the properties of these neutrinos. And so I say that they are the key to understanding many features about the origin and evolution about our universe. And therefore, I would call them a new window into our universe. And this 50 was an arbitrary number. I am sure there are more than that. Okay, experiments around the world are studying different properties of neutrinos. It just shows the interest in neutrino physics today. As I said, I want to apologize for the lack of any experimental details. I just showed a lot of data without telling you what those experiments were. Each one is a very beautiful experiment. Each one deserves an individual talk, but I could not do it. And before I end, I want to make two final remarks. So why spend so much time and energy on one particle? Any particle, need not be the neutrino. So about, 100 years is a kind of whatever, I've rounded it off. The electron was discovered. At that time, the discovery was driven by simple curiosity. People did experiments, people were trying to find out the nature or properties of matter and discover the electron. Okay, J.J. Thomson discovered the electron. Today, I am talking to you, even to you in the audience because of my mic, by means of electronics and computers, which would not be possible without discovering the electron in the first place. In 1932, the positron, you remember this is the antiparticle of the electron, the positron was discovered, for which Anderson got a Nobel Prize, but the PET scan, which all of you know about, have gone to hospitals and maybe even had experienced it yourself, the positron emission tomography scan was invented as a consequence because the P in the PET stands for this positron. Okay, so such advances in medical imaging, in fact starting from X-rays, to PETs, to MRIs, all these are actually at some point particle physics detectors, which then found their use and place in medical imaging. So they were all possible because of discoveries in particle physics. So at least to me, it's clear that discoveries in science and physics drive the development of technology. Science, engineering, and technology I think of as the three legs, which allow this constant progress to occur. Without new scientific discoveries, there is no technology to develop. And after you develop the technology, you're looking for the next big thing, so you have to have the discovery in science. So they help advance each other. The proposed India-based neutrino observatory, with its scope for interaction both with members of universities, both faculty and students, and with industry. A lot of MSMEs are involved in building various parts for our detector, is therefore an ambitious and challenging project with enormous potential for science and technology development. I want to really highlight this. So it's not simply a matter of studying neutrinos. Why study neutrinos? Because of the associated advantages that you will get, because of developments both in the detector and electronics technology and in the development of human resources with such a project. Of course, advances in basic science are also important to understand the world around us, what our universe is made of, and that brings me to my second final point. I stopped with the sun, fusion in the sun, though we stopped with helium. There's a little bit of carbon, nitrogen, and oxygen also in our sun. You can find it through a spectroscope. But in more massive stars than our sun, the fusion continues. The fusion, I think it's giving up. I will use my cursor here. The fusion continues beyond the production of helium. So for example, carbon, beryllium, and then in the next stage, carbon, nitrogen, oxygen, okay, all the way in fact to silicon and iron are being produced inside the cores of heavier stars. So our sun is just, it's a mid-sized, mid-life star. It's very, very ordinary. We belong to a very, very ordinary solar system. Hundreds of thousands of such solar systems are there in our universe. There are many stars much heavier than our sun where, as I said, particles all the way up to silicon and iron are produced, and in many of these processes neutrinos are produced as well. And finally, many of these stars, when they are so massive that they explode or they implode and then explode under their own weight, that process is called a supernova. Neutrinos are produced in such supernovae as well. They have such supernova neutrinos have been observed. Nobel Prize has been given for such a discovery, but that is not really what I want to say. So when stars die, as I said, our suddenly the cursor wakes up. Our sun is just another star, and technically now I suddenly brought a technical point. It doesn't matter. If something is heavier than the sun, it just simply cools into a white dwarf, as you can see. Our sun is here. Our sun is now 4.5 billion years old. It will gradually warm into a red giant, which will have a size which will encompass Venus and beyond, and then it will fade away into something called a white dwarf. So it's like roughly about half its life is over. It's a kind of a middle-aged star, okay? But if it has a mass much larger than that, 8 to 20 times the solar mass, then such a star collapses into a supernova, and the remnant is a neutron star. And if it's even heavier than this, there's a runaway collapse into a black hole. Now, of all these stars, and that is the question I really want to put in front of us, when we want to study these stars, when we want to study what is the universe around us, there's a beautiful periodic table which I've shown many times actually in many such talks, that apart from hydrogen and helium, which are colored blue, which were produced at the time of the Big Bang when the universe was formed, these golden and silver objects, as you can see, these elements were all produced either in exploding massive stars, which are the supernovae, or in exploding white dwarfs. And you can see these objects, for example, iron, cobalt, nickel, copper, zinc. So all these things that are there in our bodies, iron, during COVID, everybody understands importance of oxygen transport in our bodies. Without iron in our hemoglobin, that simply will not happen. The entire 100% source of this iron is coming from exploding stars far away in our universe. Silicon, aluminum, phosphorus, gallium, germanium, all the semiconductor devices, p-doped, n-doped, all of them also come from exploding stars. So all our electronics is coming or is possible only due to these elements which have been produced in the furnaces of stars in faraway parts of our universe. So as I said, the story of neutrinos is fascinating to scientists because it is tied up to the origin and evolution of the universe, but I believe that it should be fascinating for all of us because it is ultimately the story of the only universe that we have ever known. Thank you very much.
Yes, so there are some questions which have come on the YouTube channel. So while you think of some more questions here, let me read out. So a question from Hemant Kumar: how are sunspots formed in the sun?
Okay, so this talk was not about the sun itself, except to talk about the core of the sun. If you look at, maybe this picture will help. So you can see that, on the surface of the sun, there's also a magnetic field in the sun, by the way. So all this hot matter that you see, okay, the light is simply, okay, now it's visible. Okay, it just keeps flowing out along these magnetic field lines and falling back in. There are some beautiful pictures on the net you can find where you can actually see these plumes forming over here, and sunspots are just darker places where the temperature is lower than in the other places. Okay, so that these sunspots actually are studied. By the way, there is a very big observatory in Ooty in Tamil Nadu which studies the sun through telescopes and monitors these sunspots and follows them actually through the day. There's a lot of physics in that also. So basically that is coming from the surface properties of the sun. So a lot of hydrodynamics involved in it. Sorry, not Ooty, Kodaikanal, I'm sorry.
Yeah, thanks. There's another question
Thanks,
from
Tiaji.
yeah. There's another question from Samantha Roy asking whether dark matter and antimatter are the same.
It's okay. Now, this leads us to a different, see, I talked about the universe as though we know everything about it. Unfortunately, it turns out that this matter and radiation that I talked about, like the examples are the electrons and the neutrinos and the photons, which are, these photons and the neutrinos are the most abundant elements in our universe that we know, particles that we know, but they actually make up only 4% of the universe. This has been a big puzzle for physicists for the last, I don't know, maybe 20 years or 30 years now. That's because there are evidences, very, very strong evidences that massive objects like our star, like our galaxy, like other galaxies are actually surrounded by or contain some matter which does not shine like particles. So it does not contain atoms or electrons which can get heated and show up as light in X-rays or gamma rays or in the telescopes that we have on Earth. So they are called dark matter. These dark matter are not antiparticles. Antiparticles are charged. For example, a positron is charged. So it can also have interactions which emit light. It will be visible to us over here. So it is not part of ordinary matter. This dark matter is called dark because it doesn't shine in light, but we do not know anything about it except we have some idea about its mass. And we have some idea about its distribution in the universe. As I said, it is clustered around where you have massive objects like galaxies or our sun or other stars. And it comprises 25% of actually the universe. So 4% only is our ordinary matter, 25% is dark matter, and in fact the remaining 70% is something that is even less understood and is called dark energy. So this is a little bit different part of the universe I have not talked about. What I have been talking about in this entire talk is the visible universe. Okay?
At this stage, what is the most pointed scientific question that INO is trying to answer? Like,
I roughly told you, right? That is the mass ordering problem. So the thing is this, if you now, since it's a question answer session, I'll try to say it in a little more formal fashion. So I showed you a 2 by 2 matrix which is parametrized by one parameter theta. The moment I have 3 flavors, I have 3 angles and a phase. Now what happens when you have a phase, because of the nature of neutrinos and antineutrinos, is that the phase will be opposite for neutrinos and for antineutrinos. When the phase is different, then the interactions of these neutrinos and antineutrinos will be different, and this is technically called CP violation, charge parity violation. Okay. Now, if you look at what INO is trying to do, the way in which INO is trying to measure this mass ordering, whether the third mass eigenstate is heavier or lighter than the first mass eigenstate, the crux of the thing is that this particular measurement, the way in which we are going to do it, is independent of the CP phase. Now the CP phase is completely unknown. This mass ordering is also unknown. So in other neutrino experiments, for example, there's a proposed experiment in the US called DUNE. Now DUNE is going to actually be sensitive to both the CP phase and to the mass ordering, but it has to disentangle the effects of 2 unknown quantities. Whereas since in INO, the experiment will be insensitive to the phase, then you will have a cleaner measurement of the mass ordering. So that is really the unique feature of this experiment, with apologies for suddenly doing some technical details. Yeah.
The mass of neutrino, any of the 3, all of them have to be less than 0.8 electron volt.
Yes.
Is it true or?
Yes, it is. There are 2 different statements here. The 0.8 number is a different number. There is an experiment called Catherine. Okay, I will tell you more and more technical facts. So all these experiments like the solar neutrino experiment or what INO is proposing to do are what are called based on neutrino oscillation type experiments, which means that they are going to look at the mass differences of these mass states, but they will not tell you what is the absolute mass value. Whether it is a million electron volt, fraction of an electron volt, or somewhere in the thousands of GeV, we have no idea. It's not going to tell you, it's just going to tell you the differences. And the differences turn out to be very small so far. They're of the mass squared differences are of the order of 10 to the minus 3, 10 to the minus 4 electron volts squared. Whereas the mass of the electron is 500,000 electron volts. So there is difference there. So we don't know what is the zero of the mass scale. We only know the mass differences. So the zero could be anywhere. Now this experiment called Catrin, which looks at tritium beta decay, is actually looking at the direct measurement of some combination of masses, which is actually the electron neutrino mass, but it will be therefore with the phase dependence on the various mass states. It has put a limit of 0.8 electron volts on the absolute value of this mass. So this is 0.8 electron volts. However, because neutrinos are so abundant in cosmology, the question of whether the universe is closed or not will depend, because now even the neutrinos have very small mass, there are so many of them. So the closure of the universe also puts a limit. If you assume there are 3 flavors of neutrinos, cosmology tells you that the sum of the neutrino masses cannot exceed 0.2 electron volts, which is really a small number. Catrin has not reached there yet. Catrin can reach 0.2 electron volts, but it will take some time. So right now, recently, last week in fact, Catrin has put a number of 0.8 for the nu E mass. But cosmology has put an even tighter bound of 0.2 electron volts for the sum of all the masses. Yes.
Thank you. So I think on this note, okay, I can see there's one more question. Yeah. So let's have this as the last question. Yeah, last comment, okay. And
this is a comment on the CNO neutrinos from the CNO cycle. So there's been a recent measurement of CNO neutrinos from Borexino, which says that actually it's only 1% it contributes to the heat production in the sun. More precisely, 1% of the neutrinos from the sun come from the CNO cycle, which is an extremely exquisite measurement because it's so tiny, but it has been measured now. It's a beautiful result. And now the next step, of course, would be to look at PEP neutrinos and so on. That's just
Yes, very nice comment. Thank you.
thank you very much.
Yeah, so okay, it was a pleasure giving a talk to this audience after a long time in the hall. Thank you very much.
Yeah. Thank you, Indu. Join us all in thank you.